Okay, to start solutions, what we're going to talk about are a few definitions. The first one is that the solvent, whoops, what happened there? The solvent is going to be the substance that's present in greater quantity in a solution. So we talk about it as being the substance that's doing the dissolving. So a lot of times that's water. It certainly doesn't have to be. You could have an alcohol solution or whatever, really. But if you're reading a problem and you're like, well, which one is the solution or the solvent? Which one's the solute? It's going to be the thing that's in greater quantity. So that's the solvent. The solute is a substance that's present in a lesser quantity. It's the substance that's being dissolved. And when we talk about solubility, we have to understand a little bit what's going on here as far as the like dissolves like rule. Now, like dissolves like, all that means is that polar molecules are going to be dissolved by polar substances, polar solvents. So we talk about this weird little thing that it's got going on, just ignore that. What we've got going on here is, say our universal solvent is water. It's called our universal solvent. And we know from a couple chapters ago that this is definitely polar. Okay, oxygen is electronegative, more electronegative than hydrogen. And so even though they're sharing the electrons, there's this pull upward toward like this. It's V-shaped, so it's polar. So because of that, another water molecule that I could draw over here is attracted to it. So two things have to happen, and you can actually calculate this mathematically. But first of all, you have to understand how much energy it's going to take to pull one water molecule away from the other molecule. So that's going to take energy to pull these two away because they're attracted to each other. The other thing it's going to take energy is to take the polar solute or the ionic solute, pull it away from each other. And then there is a payback, and that payback is that there's going to be a connection, another type of intermolecular connection between the solute and the solvent. So if I have, for instance, an alcohol of some sort, say methanol, so here I have methanol with its carbon, like so, there is this attraction. And so there is a payback. So first of all, this water has to be pulled away from another water. This alcohol has to be pulled away from another alcohol, and that takes energy. But then there's this payback because when they attract each other, they release energy. And you can, again, calculate that, which would be for a different class. But this is what's going to happen. Ionics, same kind of thing that's going on. Now remember, ionics don't have a partial charge. They have a full-on charge. But it's still going to be the same thing. So I'm trying to dissolve salt in water. I do have to pull the Na+1 and the Cl-1 away from each other. But then what's going to happen is the hydrogen, which is a little bit positive, and the chlorine, which is a full-on negative, will be attracted to each other. The sodium will come over here and be attracted to the oxygen. And then these two break up, and you don't see the NaCl in solution anymore. And that's because they're broken up and they're binding to the respective parts of the water molecule. In the same sense, nonpolar solvents dissolve nonpolar solutes. So if you've ever had grease on your hands and you're trying to get it off with water, it doesn't work so well. You have to use some soap, which you could look at the hand washing video, which I hope you did, and that goes for grease as well. Another thing I know when we used to work in the plants, the Ford and GM plants, we would look and people would have this grease or motor oil on their hands, and they dunk their hands in a little bucket of like trichloroethylene or acetone. And these things are not polar, or they're not that polar, and they would wash off this grease. Not really healthy, but it does work because nonpolars will dissolve nonpolars. Okay, a couple other things that you need to know. A saturated solution, when a solvent contains as much solute as it can at that temperature, you realize that temperature does affect the solubility. You know that lots more sugar dissolves in hot coffee than it does cold coffee. Unsaturated, when a solvent could dissolve more solute at that temperature. So you just put a teaspoon in, you know, you could put probably 5 teaspoons of sugar in. Now, this is an interesting thing, and I'm going to upload a video too. It's called supersaturation, and it's when a solvent contains more solute than it can or should at that temperature. It's a very unstable solution. You're going to get your solution really hot, so more salt or whatever dissolves in it, and then you're going to cool it without disturbing. You're not going to, put a top on it. You're not going to jiggle it. You're going to make sure that nothing can get in it. It's not jiggled. But then if you drop a little crystal in or even jiggle it, all of it precipitates out at once. It's a little bit like superheated water. We've talked about that with bumping, the water shooting out of the test tube because none of the water molecules have it together enough to make a bubble, but then all of a sudden all of them do. It's kind of this situation. They're all kind of sitting in limbo, but then a crystal's dropped in and then bam, everything goes out. So I will upload a video of that and you should watch it because it's just fun and also educational. All right, so a couple of things we're going to look at are factors that affect the rate. Now, this is different. The rate is different than how much ultimately dissolves. But if we're talking about rate, first of all, surface area, get it smashed up into tiny little particles, and more of their surface is exposed, more can dissolve. Stirring, again, you're just having more surface exposed to the solvent. And temperature, not only will temperature affect how much dissolves, it does affect how fast it dissolves as well, because the molecules are just moving faster. Remember from last chapter, kinetic molecular theory, they're moving faster, they're more interaction, and they're going to dissolve faster, and generally more. And we're going to look at a worksheet there, because that's not always true. Actually, going back here. In fact, when I said it's not true, generally what happens is solids, that's generally, will increase with a temperature increase. So more solid will dissolve with a temperature increase. Gases actually have the opposite effect. Less gas will dissolve when the temperature goes up. So if you have ever had your pop out on a hot day, it goes flat a lot faster than it would if you had popped open on a cold day. Of course, you've opened it, so the pressure's off too, Henry's law, but also temperature affects that. So we'll look at that on a worksheet as well. Okay, so we're going to look at a few different ways to calculate concentration. Today I'm going to look at mass percent in this video. The next video I'm going to look at molarity. I love to look at molality. It's so interesting because it's colligative properties. We don't have a lot of time for colligative properties, although it is interesting. You definitely will do that in a higher level chemistry if you do that. Molality is specifically used for colligative property calculations. And so we'll talk about that briefly, but we won't do the calculations. There's other things you can do. Normality, you could do volume percent, so you don't have to do mass percent. So there are other ways. All right, so let's just look at this one that we're going to look at in this worksheet, or this video, and this today's worksheet, and that is mass percent. And mass percent is simply the mass of the solute over the mass of the solution, but be careful because this is solute plus solvent. And that would be the mistake a lot of people make by only putting the solvent here. They put the solute up there and they put the solvent down there, and that's not what you want to do. You want to put everything. It's really like any kind of percentage. If I want to say how many people are wearing red shirts today, if we're in school, we would count up the people wearing red shirts. We put them on top. We put everybody, including the red shirt people, down here. So it's no different than any regular percentage. All right, so if I am going to prepare a solution by mixing 1 gram of ethanol with 100 grams of water, the ethanol, which is present in a lesser amount, is certainly the solute. Now, rookie mistake here is to put the 100 grams down here, but I want 101 grams because it's solvent plus solute. Okay, and since it's a percentage, we would multiply by 100. If I want to keep it as a fraction, I certainly can keep it as a fraction. That's not a huge deal either. And so when you do that calculation, and I would encourage you to do all the calculations, even though you see them here, it's different. Even though this one seems pretty easy, it's different when you do it yourself. So 0.99% solution, okay, 0.0099 fraction. And if I multiply by 100, it's 0.99%. Okay, I'm going to do another one, and I don't care how you do this. I'm gonna do it kind of a long way because I think that makes more sense to people, but if it makes sense to you, you do it however you want to do it. So we're going to talk about milk, and cow's milk contains about 4.5% by mass of lactose. So if you're lactose intolerant, that is too much lactose. And so we just want to know, okay, so let's say I know this information and I have 175 grams of milk. So what do I want to do? Well, what I'm basically saying here is that for every 100 grams of milk, that's the solution. What I'm saying here is that 4.5 grams is the lactose, and that's the solute. So that's what I mean when I say 4.5%. If I want to put that in a fraction, I'm saying for every 100 grams of milk, 4.5 grams of it is going to be lactose. That's just what it means. And so I'm really a big one for dimensional analysis. So I'm just going to take 175 grams of milk, and those cancel there. Okay. And so again, I would encourage you to write that out, but we're just going to take those by 100. So what we see here is that if I have 175 grams of milk, what I'm consuming is 7.8, and around here, 8 grams of lactose. And if you want to set it up as a ratio or however you want to set it up is fine. I'm just saying, look, if I have 100 grams, I'm going to consume 4.5 grams of lactose. If I have 175 grams, which is more than 100, I'm going to consume 7.88 grams. Okay, and so that's how you want to look at that. So this is the first video, and we'll go on tomorrow to molarity, but if you understand this, just do the worksheet. We'll go on to molarity, which is a little bit more difficult, and then we're going to go ahead and do solution stoichiometry, which is even a little bit more difficult. So make sure that you're building on this.